A frisbee is a concave plastic disc designed for skimming through the air, and for decades, frisbees have been a source of entertainment for people of all ages. Frisbees can travel for large distances and seem to be able to defy gravity, but they can be explained by two physical concepts: aerodynamic lift and geoscopic stability. The purpose of this video is to create a model of the flight parameters, lift, drag, and position of a flying disc as a function of velocity and angle of attack. The aerodynamic forces lift and drag depend solely on the angle of attack of the frisbee and are perpendicular and opposite of velocity, which is one of the main reasons why a frisbee stays in the air for so long. This video will show a MATLAB solver that calculates the distance a frisbee travels with a starting velocity and angle of attack, and an ANSYS simulation of a frisbee in flight, showing the effects of lift and drag forces as well as the airflow over the disc. A frisbee experiences two major forces while in flight: drag and lift. The MATLAB simulation aims to compute these two forces and model the path of a frisbee given an initial velocity and angle of attack. The height of the frisbee is given by y, and the length traveled is given by x. Note that the height of the throw begins at a non-zero value, ho, which accounts for the fact that a normal frisbee is not released from ground level. The drag force experienced by the frisbee can be modeled by the drag equation for high velocities, initially proposed by Lord Rayleigh. The equation Fd shown here is the drag force experienced by an object moving at a high velocity. To calculate the lift force on a frisbee during its flight, the frisbee can be assumed to be similar to an airplane wing in flight. Thus, we can use Bernoulli's principle to model the lift on the frisbee. The Bernoulli principle describes the relationship between velocity, pressure, and height of two different points on a given streamline of fluid flow. Knowing that the height difference between the top and bottom of the frisbee is negligible, and the velocity of air on one side of the frisbee will be proportional to the velocity on the other side, as the frisbee itself is moving through the air at a singular velocity, we can simplify the equation. Lastly, we know that the pressure is equal to force divided by area. The lift force the frisbee experiences is directly related to the difference in pressure between the top and bottom of the frisbee. This allows us to come up with the final form of the lift force equation, FL. Knowing the drag and lift forces acting upon the frisbee, we can now derive equations for its velocity and position using Newton's second law. The MATLAB simulation uses Euler's method to calculate the velocity at the next time step as the sum of the current velocity and some incremental changes in velocity given the initial conditions. Looking at Newton's second law, F equals ma, we know the value of the mass of the frisbee, and we have the equations for the forces in both x and y components. The acceleration can be rewritten as delta v over delta t. By rearranging this equation and substituting the force expressions from the previous slide, we can come to an expression that defines the incremental changes in velocity at each time step. Similar to the velocity, the position of the frisbee at the next time step can be expressed as the sum of the current position and the incremental change in position. This incremental change in position is expressed by the current velocity multiplied by the length of the time step. Using these equations described, the MATLAB simulation predicts the position of a frisbee as a projectile flying in 2D. The solver takes an initial throw velocity and angle of attack and iterates until the frisbee reaches the ground. ANSYS Fluent is a tool used to determine the fluid dynamics around an object. To simulate a frisbee through the air, a binding box was created around a 3D frisbee model. The binding box acts as a constraint on the environment and was made to be 500 millimeters cubed. The frisbee was then placed in the center of the binding box to minimize the effects of the box on the air surrounding the frisbee. A coarse mesh was generated in order to speed up the process of solving the mesh. To simulate the disc moving through the air, the initial condition of the air at the inlet was set to 15 meters per second. By switching the frame of reference, it simulates the frisbee moving at an initial speed of 15 meters per second. Then, the initial conditions of the air and the frisbee were set. We chose the default setting for air as defined by ANSYS and determined the density of PLA through an online source. The following figure shows the configuration of PLA. When determining the lift and drag coefficients, the solver was run until the residuals were below 10 to the negative 3, ensuring that the data did not deviate by large amounts. This model assumes that the frisbee is not spinning, and so will maintain its current course. This will change the results as there is a force generated by the spinning body. For the purpose of this model, assuming that the frisbee is not spinning means that we are simply analyzing its aerodynamic properties. To collect data regarding the flight path of the disk, snapshots of the disk are taken at 10-degree increments in the angle of attack. At each step of 10 degrees, the lift and drag coefficients were recorded. Looking at this table, the lift coefficients seem to increase when the angle of attack is around 30 to 40 degrees. The drag coefficient appears to be maximized as the greater of angle of attack. Here is the drag coefficient at 0 degrees compared to the drag coefficient at 45 degrees. This video shows how different parts of the disc are affected differently by the fluid. This is useful information for the development of a model to track a frisbee. This idea will be covered in greater depths in the discussion portion of the video. We got our experimental data through recording videos of many different frisbee throws, varying the angle of attack and recording the distance traveled by the frisbee. The videos were then analyzed to find angle of attack. And we also determined the starting velocity by dividing distance by time. Since the purpose of this project is to find the distance traveled of a frisbee with respect to angle of attack, in order to improve our frisbee skills, we need to see how our frisbee throwing data compares to that of the simulation. Obviously, when throwing a frisbee outdoors, there will be other variables affecting the path of the frisbee, and since our experimental data collecting process includes someone manually tossing the disc, the speed and method they throw is bound to be inconsistent. However, even with the error we incur, the data should be accurate relative to itself, meaning that the distance traveled at a 45-degree angle of attack should be smaller than that of the distance traveled with an angle of 10 degrees. And by looking at this plot, this seems to be true. The MATLAB solver that implements Euler's method was used to plot the flight path of the frisbee given initial throw velocity and angle of release. The plots shown on the screen now are the results of the MATLAB solver given an initial throwing height of 1 meter and an initial throwing velocity of 15 meters per second. It is seen that the flight path of the frisbee follows the same general shape for angles between 10 and 40 degrees, which is the general range from a natural backhand or forehand frisbee throw. For the first portion of the flight, the frisbee flies almost linearly as it climbs. The large horizontal velocity results in a larger drag force experienced by the frisbee, which begins slowing down the frisbee immediately after it's released. The slight upward angle initially provides a small amount of lift force, which in turn begins to raise the front end of the frisbee. As the frisbee angles upwards, a large amount of its surface area is perpendicular to the horizontal velocity, which further increases the drag on the disc. This feedback continues until the frisbee reaches the apex of its flight, at which point the frisbee stalls and falls to the ground. This behavior is clearly visible in the video shown. These plots show the distance traveled by the disc as a function of the initial angle of release. Note that the data points for the MATLAB simulation are using an initial velocity of 15 meters per second, and the experimental data was also constrained to the same initial velocities to the best ability of the thrower. It can be seen that the general trend in the data is consistent between the MATLAB solver and the real-life experiments. The distance achieved increases up to a maximum at an angle of release of around 10 degrees, where the relation between the drag and lift forces caused by the angle of release is optimal. As the angle increases further, the distance begins to drop again, coming back to the original 0-degree value at around 30 to 35 degrees. Although the general shape of the trend is similar, the actual distance traveled by the frisbee is greater in the experimental data than in the MATLAB solver. This can be attributed to the errors produced by the simplifications made when solving for the lift and drag forces and their coefficients. In actuality, a frisbee is not a perfectly flat disc. The lip and rim influences the flight of the frisbee, and this influence is lost in the MATLAB solver. Environmental factors are also a cause for the discrepancy between the results. There was a small amount of wind present during the experimental trials, which introduced an extra force that influenced the frisbee's velocity during its flight. ANSYS was used to determine how the disc moves in the air at different points. It also analyzes how the disc interacts with the surrounding air when released into the wind at 15 meters per second. This data is used to determine how the frisbee will react when different angles of release are used. From the diagram, we can see that as the angle of attack gets steeper, drag is created from the increasingly large surface area facing the inlet of the simulation. The light dark blue lines represent the slow-moving air. At a release angle of 0 degrees, we can see that the air travels around the disc relatively evenly. The air above the disc is not deflected, as such lift is not generated. Looking closely at the diagram, one can see the currents that form underneath the disc. This creation of current creates drag in the system. As the angle of attack increases, the drag will increase, as will the lift generated. At larger angles of attack, the deflection of the air above the disc increases. This deflection of air creates low-pressure pockets, which correspond to a force perpendicular to the flow of air in that region. Looking at this clip of a throw, we notice that from the time the disc was thrown to the time of landing, the angle of attack gradually increased. It can be estimated that the disc traveled through 0 to 30 degrees in terms of angle of attack. The path of the disc can be explained with the fluid flow over the disc at various steps in the video. Upon release, the disc had an angle of attack of 10 degrees. Looking at the 10-degree ANSYS simulation, we can see that there is a pocket of slow-moving air above the disc, creating lift. The tail of the frisbee is disrupting the airflow, creating drag on the tail end of the frisbee that acts as a moment about the center of the disc. This lift and drag combination will cause the frisbee to increase in elevation and at the same time start rotating upwards, increasing the angle of attack. Eventually, the angle of the disc reaches 20 degrees, which is replicated by the current ANSYS simulation. Looking at the figure, a strong drag force is created at the tail end of the disc, shown in dark blue, which means that the disc will continue to slow down. The deflected air creates a pocket of slow-moving air, which in turn leads to a greater lift. When the frisbee reaches its peak prior to its stalling, the frisbee attains the largest angle of attack. Looking at the ANSYS simulation, the drag at the tail has increased even further and the lift being generated is increasing. However, the ANSYS model does not take into account the slowing of the frisbee as it travels through the air. So in reality, at this point, the frisbee would have reached a condition where the force of drag and gravity overcome the lift and initial propulsion, causing this frisbee to stall. When the frisbee stalls, it has lost its momentum and begins arching towards the ground. In the video, the release has been curved, and so upon reaching stall, the frisbee orients to the angle of least resistance and proceeds to sink rapidly. The experimental data confirms both the MATLAB solver and the ANSYS simulation. The ANSYS simulation helps visualize the relation between the angle of the disc, the velocity, and the pressure of air flowing around it. These pressures provide the lift and drag forces, which change depending on the angle of attack. The relations between the angle of attack, drag, and lift are similar between the ANSYS simulations and the coefficients calculated using the equations in the MATLAB solver. Both of these methods demonstrated consistent frisbee behavior, which is also further validated by real-life data. How does modeling a frisbee help? Well, as competitive ultimate frisbee starts gaining more popularity, broadcasters like TSN might be interested in recording the matches. To accurately mark a disc with a camera, a predictive algorithm is needed for following the disc with minimal jitter, thereby improving the viewer experience. Knowing how the frisbee behaves can also help players learn the path of the disc better in order to make better plays. For example, our findings show that if you release a disc with an angle of attack around 10 to 12 degrees, the distance traveled of the frisbee is maximized. As our understanding of the flight mechanisms of frisbee-shaped objects improve, we may also discover applications in which disc-like geometry is optimal for flight. This scope is not only limited to entire vehicles. Similar to the manner in which individual components of an airplane are designed in relation to where on the plane they will be placed, one could use disc-like geometry to design a specific part of a vehicle in order to optimize the aerodynamics of the vehicle as a whole. In early 2016, Samsung patented a new aerial drone design that closely resembles a frisbee. Further studies into the mechanics of frisbee-like objects serve to improve and advance the possibilities of technology.
Good. I said it. I was I was like, what are you doing? I threw it at you.